Any questions at all over anything, or things going all right? Yes. Sure. Oh, let's see if we can pull it up real quick. Hello. There's the new one, and if you got the other. Okay. All right. So. Nope, that's the wrong folder. Was it getting the function set up? Was that the issue? Okay. All right. So here's the new assignment too. Here's the new assignment. Yep. So hopefully this one reminded you of a Calc 1 problem, because that's kind of the problem it was. So you may have had to go online and find a tetrahedron formulas. Thank you. But you've got some given quantity, and you want to either maximize or minimize a different quantity for the same object. So you've got a sphere and a tetrahedron. Pardon me. You've got paint to cover the outsides of them, and you're going to determine the dimensions that minimize the volume of the solids. So first thing that we probably want to do is write down a function that we want to minimize. So you got a volume of a sphere and a volume of a tetrahedron. So sphere, I don't know, I'm drawing it because I don't really need it. But tetrahedron is basically a pyramid with a triangular base. The special thing about tetrahedrons, of course, is that they're regular solids. What regular means is that each of the sides is an equilateral triangle. If you play dice games that involve four-sided die, that's a four-sided die as well. All right, so for a sphere, to figure out its volume, we need its radius. For a tetrahedron, to figure out its volume, we need its side length. Those most likely are not the same. Could be, but probably not. For a sphere, the volume is 4/3 pi r cubed. For the tetrahedron, like square root of 3/12a cubed or something like that. Okay. We want total volume. So what do we want to do with those two quantities? Add them, yeah. So we want to take the 4/3 pi r cubed and add the square root of 3/12a cubed. So that's the function that we want to minimize in this case. What's the problem with it the way it stands? Yeah, exactly right. There's two variables, right? And I asked you to use the golden search method. How many variables did we have in our functions for the golden search method? Just one, right? So there has to be some other way to get rid of one of the variables in terms of the other. And that's going to be the other piece of information that you were given for surface area. We know that the surface area has to be 12, right? So if we go for our sphere again, the surface area of the sphere is 4 pi r squared. By the way, what's the calculus relationship between volume and surface area of the sphere? Side note, what's the relationship? It's a derivative, right? Which is not a huge surprise Because if you think about how your volume is changing, if you think about your volume changing, it would be proportional to the surface area. Right? So it's not a huge surprise that the derivative pops up there. For a tetrahedron, oops. It's like square root of 3a squared. Formula for the area of an equilateral triangle given its side length is square root of 3 over 4 times the side length. And then you have 4 of them. That was actually not bad. If you remember some geometry, I know. If I have an equilateral triangle, what does that height do to the bottom side? What's it do to the sides here? What's the relationship between this? What's the measure of that with respect to that? Yeah, they're equal, right? It splits it right directly in half, right? And it also splits this angle in half. If it's an equilateral triangle, what's the measure of this angle down here? 60, thank you. So the measure up here would be 30, right? You got a 30, 60, 90 triangle, right? So I can figure out the height in terms of my side length using our 30, 60, 90 relationships, right? This would be s times square root of 3 over 2. Because this would be 1/2 the side length over here, if this is your side length here. And then how do you find the area of a triangle? You do 1/2 base times height. So I'd have 1/2 times the side length times the height. That's where the square root of 3 over 4 comes from. And then I've got 4 of them for the tetrahedron. So that's why it's square root of 3a squared. Not necessarily germane to this problem if you just looked it up. But all right. So going back over here, now we have an equation that relates A and R. So now you can solve for one of them in terms of the other and plug it back into your original formula. It doesn't matter which one you solve for. But you can solve for one of them. We'll just solve for a squared. That would be a squared. So then your volume in terms of the radius would be 4/3 pi r cubed, pardon me, plus root 3 over 12 times 12 minus 4r squared over, pi r squared over root 3 to the 3/2. Since it was a cubed, I had to do the 3/2 power. And then that's the function that you want to take the minimum of. Is that okay? Is that what you needed, Lennon? Was that part? It's a little bit more complicated than a Calc 1 problem you've probably seen because you probably don't have all those nasty fractions and things in there. But it's essentially the same concept, right? You've got a function of 2 variables. I don't know how to maximize or minimize a function of 2 variables from a Calc 1 perspective. So you get rid of one of the variables in terms of the other. And then we didn't actually do a derivative at all if you're using golden search, right? You're trying to bracket at that point. Is that okay? It'd do a little bit of investigation, I'm guessing, to get your formula. But the formula you could actually derive as well if you remember what your formula is for the volume of a pyramid. Volume of a pyramid is 1/3 area of the base times the height. You have the area of the base, so you just have to figure out what the height is. And that would work as well. Other questions? Got the piece of the plastic that was sticking out, it was cracking, right? Other questions? Other things okay? The other problems okay on the homework? Okay, cool. All right. Well, let's continue on with our discussion of. We talked about representing numbers last time using our floating point representation. Talked a little bit about kind of the smallest-ish number that we can actually represent using our floating point representation. The smallest normal number that you can represent, and then you have the subnormals that you can do after that. Pardon me. We also talked about the concept of machine epsilon. What was that again? What was the definition of machine epsilon? Just to remind ourselves. Yeah, it's the smallest number that you add to 1 and actually change 1, right? Okay. So again, remember that your machine epsilon we write it epsilon sub. Usually you write it as epsilon sub MACH for machine epsilon. It's the smallest positive number. Oops. Such that 1 plus epsilon is actually greater than 1. It's the smallest possible thing that you add to 1 and actually change 1. So that makes making really, really, really small quantities hard to represent, especially if you're adding or subtracting those to or from other quantities that are much larger in magnitude, right? So you've got to worry about such cancellations, if you will, of really things that are really small. So just as a general, and this is stuff we're going to come back to later as well, but just as a kind of a general idea, if you're subtracting, that can cause bad things. So just to give you a quick example of that, maybe your machine, you don't have a very good machine, maybe it only holds, say, 6 significant digits. Okay? But if you've got something there that are longer than that, maybe you've got something like 1.00021, and you want to subtract 1.00019, you get 0.00002. You've only got 1 digit now of significance. You've lost the others. You get a lot of cancellation. And so, like I said, we'll come back and talk about this idea a little bit more in depth later, hopefully. But basically, when you've got formulas that involve subtraction, they can be bad. Okay? You'd rather not subtract if you can avoid it, because you get a loss of significance on the end. That can cause bad things. Sometimes it's even called catastrophic cancellation. We'll see an example of that today when we run something here, and I'll run some code for you here in a little bit. We will talk, and we will also come back to this in a week or so when we talk about doing some row reduction ideas and talk about how you can choose your pivots in your row reduction a little bit better so you don't lose as much in significance. We'll try to avoid cancellation if you can. Like I said, we'll talk about this more in depth later. All right. But anyway, the idea behind all of this is that in general, you can't represent numbers exactly, especially decimals, in the computer. So you're always going to get errors. Okay. Those kind of errors that come up with the representation of the number, those are what are referred to as rounding errors. Okay. So that's one form of error that you get, is what's referred to as a rounding error. That's when you just run out of digits that you can put on the end. It literally has to get rounded off. There's another kind of error that pops up that's referred to as truncation error. Truncation error comes up with using an approximation for an exact value. It's not due to the representation of the number. It's due to the algorithm that you're using to try to compute the number you're after. Okay? So let's say it's an error in using an algorithm to approximate a value. That's truncation error. Let me give you a very simple example of where truncation error pops up that you've already done in calculus class. Okay? So as an example here, you have estimated the derivative of a function at, say, x equal to a with f of x plus h minus f of x all over h, right? You've done that. Okay. Even assuming you were able to calculate f of x plus h and f of x and h exactly, and the division exactly, even if you assume you can do all of the operations exactly, that doesn't give you the true answer of the derivative in most cases. Right? So even with perfect computation, there is an error that pops up. That's truncation error. Okay? Has nothing to do with the representation of the numbers themselves. Okay? The numbers can be represented perfectly. All of your computations can be done perfectly with infinite precision, and you still get a wrong answer. That's truncation error. Does that make sense? That's different than rounding error. Rounding error comes up from trying to represent the number on the computer. I've got to cut it off somewhere. That's rounding error. Okay? Truncation error is even with perfect computations, I still get an error. Okay? Those also pop up from being able to represent things on the computer, right? For example, if I want to take the derivative of e to the x, I can't represent e to the x on the computer, right? There has to be some method that approximates e to the x where you're going to have to cut off something that's truncation. Okay? Does that make sense? Let's see where that comes from. And this is going to require us to remember a little bit of calculus. I know, I'm sorry. Okay? A little bit harder calculus even. It's power series, and I know all you love power series so much. Okay? All right. Let's review it a little bit. Talk a little bit about Taylor series. Remember, power series are infinitely long polynomials, right? Okay. So Taylor series for f of x centered at x equal to a. All right. So if I want the Taylor series for f of x centered at x equal to a, I have this part comes in because, well, if I plug it into my power series, the function values have to agree, right? And then the next part comes along and says, well, if I plug it into my power series, I want my derivatives to agree. And then the next part says I want my second derivatives to agree. And the next part comes from along that says I want my third derivatives to agree. And in general, the nth term is the nth derivative at the value over n factorial x minus a to the nth. Does that look familiar? I'm saying you remembered it. I'm just asking if it looks like something that you've seen. Unfortunately, you haven't seen it? Okay. No. Okay. Well, we'll talk about it a little bit. All right. So, you haven't seen it. We'll talk about it here for a minute. I'm going to put my highlighter on here just to ignore what I just highlighted. Okay? Let's look at the first part. That I'm sure everybody has seen. What is that, the equation of, if you just look at the right-hand side? It's a Calc 1, Chapter 2 topic. What is that the equation of if I replace the f of x with a y? Okay, so that's that idea. There's a slope idea in there. What's that? If I replace f of x with a y, what is that the equation of? Just from an algebraic concept. If I replace that with a y and a is a number, what is that equation of? It's a line. Since I have a derivative in there, what special line do you think that might be? That's a tangent line, yeah. So this, if I cut it off right there, that's a first order, call it a first order approximation for the derivative of the function. Okay. So notice in this case, this is another way to write that f of x plus h plus minus f of x over h idea. If I solve this for f prime of a, you see that slope of the secant line idea in there, right? Should also remind you of mean value theorem. Right. This is another way to approximate a derivative. The way the f of x plus h minus f of x all over h idea just comes in there by replacing your x with a plus h, essentially. All right. So I said ignore the last parts on there. Let's keep going. Where do these other pieces come from? Well, the way you create a power series is you just keep extending your polynomial approximation to the function. This is a first degree approximation to the function. It's the tangent line, right? How did you make the tangent line? You made the function agree and the slope agree, right? To get to a quadratic approximation, you make the second derivatives agree. We want a polynomial. If you want a quadratic approximation, you would want a polynomial y equals ax squared plus bx plus c, so that f of a equal, let me call it y of x here, just so I emphasize that it's a function. I want the function values to agree. I want the first derivatives to agree. And we want the second derivatives to agree. That gives you a tangent quadratic, if you will, versus a tangent line. Well, let's see what the coefficients have to be. I didn't make this polynomial very nice, so let me adjust it slightly, and so you don't have to erase it. I'm just going to write it above it. To make my computations nice, let's center the polynomial at a. Why did I do that? What do the first two terms become if I plug in a for x? Not a trick question. What is it could become? 0, right? So it makes those things go away, right? So if I want this to be true, then my c has to be the function value at a, right? Because the a times the, I used a in two different contexts. You jerk. Well, for those of you who just had me last hour, what are you supposed to do? There we go. Good. Boo. Here, I'll fix that. I'll call it a D. I used A in two different contexts, sorry. All right. So obviously if it's going to be a tangent anything to a curve, it has to touch the curve at that point, right? I need the function values to be the same, right? If it's going to be a tangent line, I need my derivatives to be the same. Well, if I look at my polynomial here, my derivative will be 2d times x minus a plus b, right? I'd bring down the 2 in front for the first one. That is the derivative, right? So what do you get when you put in a into the derivative? What answer do you get when you put an a into the derivative over here? Just b, right? So your b has to be f prime of a. What do you get when you take the second derivative? Well, the second derivative is just 2d, right? If I make my second derivatives match, whoa, that got really big in a hurry. Sorry about that. If I make my second derivatives match, then my 2d has to be f double prime of a, which means I have to divide both sides by 2. Okay. Let's go back up. See where this coefficient is? Same thing, right? Or those coefficients pop up just by making your derivatives match. What happens when you take your derivatives? You keep bringing down the power in front and decreasing it each time, right? And so I'm going to have to divide out by that number. So really what I've divided down to the bottom is 2 times 1. What do you have to do in the next one? I have to divide out by 3 times 2 times 1, or 3 factorial. The next one would be 4 factorial. The next one is 5 factorial, and so on down the line. So each power is just getting a better and better polynomial approximation at the point. You get a quadratic approximation, a cubic approximation, a quartic, a quintic, and so on up the line. And I just said the words because they're fun to say. All right. Anyway, so you can think of a power series centered at a point as an infinitely long tangent polynomial in some sense. Now, can I represent things infinitely long in a computer? No, I can't, right? You have to chop it up somewhere. And not every function is a polynomial, right? So no matter what, if you have a function that cannot be represented exactly as a polynomial, it's never exact in the computer, no matter how good the approximation is. Okay? Again, that's truncation error. Why do we call it truncation error? Well, I mentioned mean value theorem before, right? Let's think about that approximation for our derivative that we talked about, the f of x plus h minus f of x all over h. Okay? So let's think I have a power series. Let's center it at a so that we do it a. If I do f of x, then I have, pardon me, we have f of a plus, well, let's just f of a, doesn't matter. I'll do it this way to start with, and then I'll fix it. Oops. All right, so that's our power series, just to copy it down. If I want f of a plus h, we'll start there. Okay? If I put this into the power series, this is what's going in for x, right? So I'm going to get f of a plus f prime of a times, we'll write it as a plus h minus a. Leave it there. And then f double prime of a over 2 a plus h minus a squared. I'll write out one more. a plus h minus a cubed, and so on down the line. Now, you may have already simplified it when you're writing things down. What inside of each of those parentheses, here, here, and here, what does that simplify to? H, right? So I'll just write this as f of a plus f prime of a times h, f double prime of a over 2 times h squared, f triple prime of a over 3 factorial h cubed, and so on. Okay. All right, so now let's do f of a plus h minus f of a. Looking at your power series. What does that do if I do f of a plus h minus f of a? Yeah, so it gets rid of the first term, right? So we have f prime of a times h plus f double prime of a over 2 times h squared, f triple prime of a over 3 factorial h cubed, and so on down the line. And now, the last step for this one. If I want to make an approximation for the derivative, I would divide by h, right? What do I get at the right-hand side? Well, I really do get f prime of a, and then I get a bunch of other stuff on the end. Right? It'll divide out the h on all those other pieces. Look at the part that I put a box around. That's one of our approximations for the derivative, right? We agree with that? If we use that approximation for the derivative, we leave off a crap ton of terms. Technical math term, crap ton. Okay. We hope that's small, right? If h is small, that should be pretty small, but if h is big, that could be really bad, depending on the function. Right? Okay. So this is the part here. If I'm using this to calculate my derivative, this is a method that's not quite accurate because we've truncated all these terms up. That's the truncation here. Okay. Now this is where something that is akin to the mean value theorem pops up. Remember your mean value theorem back in Calc 1 said that if you have a differentiable function, there is a point in the middle where the derivative is equal to the slope of the secant line. Instantaneous rate of change somewhere equals the average rate of change on the interval. There's an analogous theorem referred to as Taylor's theorem that says that this piece I left off is equal to pardon me, some constant in the second derivative, which usually they use a xc. One of a colleague I've had called it a tornado. Don't worry about it. It's just a Greek letter times h, somewhere along the lines. There is a constant. This number here is somewhere in your interval. So this is between a and a plus h. There's a spot somewhere in your interval that if I do the second derivative at that point and multiply it by h, it equals all of that mess. Somewhere in there. Okay? Don't worry about why. I mean, we're expected to do the y. It's analogous to the mean value theorem for power series called Taylor's theorem. Okay? The important thing here is that this is a constant. There might even be an n factorial in this piece. It doesn't matter. There is a constant times this h. That's how little worried I am about the theorem. It's the times the h piece here, right? That h is kind of your error for your input idea, right? It's how far you're getting away from the point of tangency. Okay. So the error depends on what that h is. Since it's h to the first power, if you've seen some of this in computer science, this is called on the order of h. You might call this O of h. That's talking about the error. So all this means is that the error is on the order of h. Okay. Since it's to the first power, we call this a first order approximation. Okay? That's all we need. All right. By the way, this is not the only way to get an approximation for the derivative. And if you want other approximations, you might want them better than just first order. Okay? All right, so let's talk about some other methods that you might get. By the way, this is what's referred to as the forward difference. Approximation. Because you did a plus h minus a, essentially, in the numerator. Okay. Any guesses on what the backwards difference might be? Let's think about the picture, and then maybe you can guess what the backward difference is. Function. Here's a. We moved over a little bit and try to approximate with a line, right? We went from a and went forward. Any idea about how we might get backward? By going backwards. So instead of a plus h, we'd have a minus h and find that slope, right? That's what backward difference formula is. So the backward difference would be f of a minus f of a minus h all over h. Rather than going forward to a plus h, you go backward to a minus h. This is also on the order of h for the error. It's a first order approximation. It's fine, depending on the function. But a lot of time in numerical analysis is spent on trying to make your error better and trying to make it faster. Okay? We talked a little bit about faster when we did root finding, right? Newton's method was faster than bisection. Right? So we want to try to make this better and maybe faster as well. And faster in this case would be, I want my error to get smaller faster, right? If I can make a second order approximation, that's better, okay? So let's see if we can find another one that might have a better error approximation. Forward at a said, go from a to a plus h. Backward said, go from a backward to a minus h. Any thoughts about what the central difference might be? Say again? Half? Okay. Yeah, there is a half that pops up. What do you think needs to be in the center? A. If it's going to be the center difference at A probably needs to be in the center. So you're going to go forward and backward at the same time and put A in the center. Okay? So your central difference is f of A plus h minus f of a minus h, and this is where the half comes in because your length is twice as long. Okay. Let's see what the error approximation is on this. Okay. So we're going to go back to the power series and see if we can find out what the error is. It's O of h to what power? What order difference, what order approximation we have. Okay, so we already wrote out f of a plus h earlier, right? I'm going to put one more in there, just for good measure. That was what we got for the power series when we put in A. Yes? Agree? Okay. Or put in A plus H. What do you get? Ooh, darn it. Stop it. What do you get when you put in A minus H instead? Remember, just to remind, that's where that H came from there. That H squared came from, right? So notice again, remember this part was the X, right? So instead of having a H, I mean, it looks the same here. Instead of having an H squared in that term, what would you get when you put in A minus H? A negative H. Now for the squared, it'll still be the same, right? But you'd have actually a negative H inside the parentheses, yes? Yep, okay. So what's that going to change? Does that change the first term? No. Does that change the second term? Yes, it changes it to minus, right? Does it change this next term? No. Does it change the next term? Yeah, it does, right? It makes it a minus. Does it change the next term? Well, no, it's an even power, right? It's going to make every other term negative, right? Makes every other term negative, doesn't it? Now, remember, it's really, 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 really easy to lose track of the force because you smacked your head into a tree. Okay? Let's keep track of what the heck we're trying to find here. We're trying to find an approximation for the first derivative, right? I know what the answer is that I want at the end, but if I want an approximation for the first derivative, what I want to add those two quantities together. The way they're written out, what I want to add the two quantities together. If I want an approximation for the first derivative, what I want to add those things. No, the first derivative would cancel out, right? If I want an approximation for the second derivative, that wouldn't be such a bad idea, right? But I don't want to try to use this for an approximation for the first derivative, right? I wouldn't want to add them. Well, what I want to do instead? Subtract them, right? I want to subtract those two things. So when I take f of a plus h minus f of a minus h, what happens? What happens here in this first? What happens right here? Those cancel, right? What happens right here when you subtract? Cancels. What happens right here when you subtract? Cancels. The only things that are left are the odds, right? So you would get 2 f prime of a h plus, there's 2 here as well, h cubed, and so on down the line. The important thing is there's an h cubed in the next term, and everything above that is a higher than an h cubed. Okay? So I didn't write anything else. That's the important term that I'm worried about. Okay? Again, I want an approximation for the derivative. Now I'm going to solve for the derivative. I would need to divide both sides by 2h, right? Okay. So I do f of a plus h minus f of a minus h divided by 2h. I get f prime of a plus other stuff, big O notation, other stuff on the order of what? Power of h. Well, I divided the h out here. I would have to divide the h out all the way here. What's the smallest power of h that you see over here when I divide out the h? Squared. So this would be on the order of h squared. Is that better than just on the order of h? Think of h. I know when you do stuff for computer science before this class, you're probably thinking of big numbers. We're doing the reverse and thinking of small numbers. Right? On the order of h, is that better or worse than on the order of h squared if h is small? Which one's better, h squared or h? H squared, because if it's a small error, then I squared, it makes it even smaller, right? So this is a better approximation. Okay, so the centered difference is a better approximation. So let's see a demo of that real quick. Hopefully this will help a little bit. And if not, we'll try again later. Okay. You won't need to type up anything here because I've got it all put in here to start with. What this is going to do is calculate the different formulas that we just talked about for approximating derivatives. We've got a forward difference method, we've got a backward difference method, and we've got a central difference method. Okay? Centered, central, centered, it doesn't matter, the same word. Okay? To be able to test this out, I need a function and its derivative. You can type whatever you want here, but you actually have to know the derivative to be able to test and see what the errors look like. Okay? So this first function that I put in here is just the sine of x minus x squared plus e to the x. And you can check my derivative, that the derivative should be cosine of x minus 2x plus e to the x. Again, remember using numpy here, and you can put the np in front of each of those. So those are functions to call. Okay. So all it's going to do is it's going to calculate the forward difference, the backward difference, the central difference for different h steps, and calculate the errors and see what happens. Okay. Since these numbers are so small, and it's going to make the steps go down by dividing by the same amount each time, it's going to put it on a log scale, so you don't see a bunch of things crammed. It's going to make it more linear. Okay. So just to show you what this looks like for this function, and we're going to change this to different functions as well. So, and again, full disclosure, I let some AI program write this as opposed to me. Okay. You can see the errors. So what this did is it plotted these different things. So you need to read this from right to left because the values for h are getting smaller. So it's getting closer to 0, and closer to 0 will be to the right. Okay, so the orange line here and the blue line, which are on top of each other, that's representing the error in calculating the derivative value using the forward and the backward difference methods. Okay. The green one is using your centered difference method, your central difference method. Now again, this is log scale, so what that means is that these tick marks here are changing by powers of 10. So going from this tick mark to this tick mark, that's actually 100 units, right? But going from this one to this one, that's another 10, well, it's another 100. But anyway, it's smashing them down. It's spreading things out that get smashed down quickly. Okay. All right. Notice in your centered difference method, the error gets smaller quicker than it does in the other two, which is what you see. Except what happens? I get here this error here and here are starting to get small, and then it goes back up again. Thoughts on what happened? Why did the error get worse after a while? In particular, let's think about this number right here for the error. What's that about? Looking at the graph. Yeah, that's exactly what's happening. This is about 10 to the negative 8th, right? Which is about half of machine epsilon. And we've got 2 of those computations that are going on. The cancellation's coming up and we're hitting machine epsilon, and it's making the error worse because we're getting rounding error. So this side here is representing your truncation error, and then this side over here is getting your rounding error. And we're starting to get rounding errors at that point because of the representations. So it's great for a while, and then it starts to get worse. I mean, it's still not horrible over here, but it starts to get worse because of the machine representation of the numbers. So anyway, you can actually go through and figure out what those points are supposed to be. And it does turn out to be half of machine epsilon if you make some assumptions on what's going on. And it really does bottom out there at about half of machine epsilon. It goes back up again. You can treat it like a calculus problem. All right. Anyway, moral of the story, no matter what you try to do, we made a better method, right? We got a better method that got better approximations more quickly, and it still, at some point, is going to get bad. Right? So there's always going to be some error in no matter what calculations you do. Okay? Even if you have infinite precision on an exact method, that method inherently has some approximation in it. And then you can also think about what happens if you start getting data that's going to have errors in measurement, for example. Then you've got another introduction of error, right? You're going to have some variance. You got some noise. You got all sorts of things that might pop up. The moral of the story is you need to keep track of your errors and where they might come in. In any event, the process okay for how we developed this was being a second order method versus a first order. Okay. All right. So we'll talk more about errors later as well, but I want to get into. It's interesting. I'm still recording, right? Yeah, okay. Still going. I was just making sure I was still recording and it didn't get shut off, since I don't see my pause button in the lower left-hand corner anymore. So, all right. Anyway, let's talk about other types of approximations that you can do. All right. We're going to come back to approximating derivatives, and we'll also do some approximating of integrals here in the near future. But for right now, let's just talk about trying to approximate functions, okay? We've already talked about this a little bit, as we mentioned above. One of the easier types of functions that you can use to do approximation are polynomials. So what we're going to talk about today is how we can do what's referred to as polynomial interpolation. Right. So let's just start with an example. Maybe. My textbook is 3-hole punched in a binder, so I don't want to bring the whole binder with me. So, all right, this is number 2 in chapter, looks like 17. All right, so they just give you some points. I'm just going to write it as a table. They write it slightly separate. They write it horizontally. Your x's are 0, 1, 2.5, 3, 4.5, 5, and 6. And then your y's are 2, 5.4375, 7.3516, 7.5265, 625. They give us some nice numbers here. 8.4453, 9.1875, and 12. Okay, great. I should have just made up some numbers for the first example rather than pull them out of the book, but that's okay. It's not like we're going to do it by hand. All right. Looks like there are 7 points there, right? The idea behind polynomial interpolation is to find a polynomial of the smallest degree possible that will go through all of those points. That's the idea. Okay. So let's think about a linear polynomial to start with. Probably the easiest one. I mean, constant polynomials, but they're not very interesting. Linear polynomial. How many coefficients do you need to know before you're guaranteed to have the linear polynomial? How many do you have to know? Think about what your equation looks like. How many coefficients do I need to know? So let's say, what's kind of the general format that you think of for your line? What's the first? Let's not say general. What's the first format that you think of typically when you think about an equation of a line? Mx plus b. What do you need to know? The m and the b. So I need two of them, right? So I need to know two coefficients, right? If you have a quadratic, how many coefficients do you need? Three. I need an a, a b, and a c, right? If I think of ax squared plus bx plus c, I need three, right? If I have a cubic, I need four, right? And so on up the line. So it's always one more coefficient than the degree, right? Okay. So now let's think about it from a solving a system of equations perspective. If I have two unknowns in the line case, how many equations do I need to make sure I get the two unknowns? Two. If I have three unknowns in the quadratic case, I need three equations. I need the same number, right? Okay. How many data points do we have here? We've got 7, right? With 7 data points, I can make 7 equations. So what's the polynomial we can do? We can make sure that I get through all the points. Better be a degree 6, right? This 6 degree, 7 coefficients, right? Okay. And then 7 data points will give me 7 equations. Okay. All right. So our goal here we want to find a 6th degree polynomial that passes through all these points. That's the goal. Now again, general equation or a general form of a polynomial would look like y equals, I'm going to write it going up in degree rather than going down in degree, so I'll write it as a0 plus a1x plus a2x squared plus a3x cubed, a4x to the 4th, a5x to the 6th, a6x, to the 5th. I don't know why I wrote to the 6th and to the 6th. Okay. Using subscripts rather than different letters for the coefficients. I need to figure out A0, A1, A2, all the way up to A6. I have 7 things to find. I need 7 equations. How can I use the 7 data points to get me the 7 equations? Okay, let me ask you this. If I want to make sure the polynomial passes through those points, when I plug in 3 into the polynomial, what do I want to get out? Yeah, I want to get the y value, the 7.5625 in that case, right? If I plug in 6, I want to get out 12, and so on up the line, right? So how am I going to create my equations? What do I need to do? You just plug everything in and set up the equations, right? In the first one, you would have, well, you put in 0 for x, you get 2 equals a0, right? We agree? Okay. And the next one you have 1 equals A naught plus 5.4375 A1 plus 5.4375. Ooh, I'm doing it backward. Sorry. I'm putting my X's. I flip-flop my X's and my Y's. What are you supposed to do? Oh, thank you. A1 times 1 plus A2 times 1 squared, A3 times 1 cubed, all the way up to A6 times 1 to the 6th. There's a reason why I left them as 1s and not just wrote the equation. The next one, you would have 7.3516 equals A naught plus, pardon me, A1 times 2.5, A2 times 2.5 squared, A3 times 2.5 cubed, all the way out to A6 times 2.5 to the 6th. Noticing a pattern? Okay. Let's think about it in terms of coefficients. I mean, if you've had linear or taking linear, there's a connection between these two things. Okay. Think of these as coefficients. What for every single A naught that we have, what's your coefficient going to be? 1, right? So if I start gathering this as a matrix, your first column is going to have a bunch of 1s. And we had 7 equations, so I better have 7 1s go down that way. What is your coefficient on the A1 every single time? The x value, right? So the first x value is 0. The second one is a 1. The next one is a 2.5. You'd have a 3, a 4.5, a 5, and a 6. What's the next one going to be? Those squared, 0, 1, 2.5 squared, 3 squared, 4.5 squared, 5 squared, 6 squared, right? If I keep going, the last column is going to be all those things to what power? The 6th, right? 0 to the 6th, 1 to the 6th, 2.5 to the 6th, 3 to the 6th, 4.5 to the 6th, 5 to the 6th, 6 to the 6th. Okay. And you can keep going with this. This matrix has a special name. It's referred to as a van der Waals matrix. Again, for those of you in linear, or for those of you who have had linear, when you solve a system of equations, what are your possibilities for the number of solutions? You have 3 possibilities. How many solutions can you get for a system of equations? Yeah, 1, 0, or infinitely many, right? That's the only possibilities you get, right? You get no solution, you get exactly 1 solution, or you get infinitely many. We don't want the infinitely many or the no solutions. They pop up, but we don't want that. We want the exactly 1 case, right? Okay. So thinking about it in terms of row reduction, this matrix is going to be square, right? We forced it to be square. Same number of equations as we have unknowns. We forced it to be square. So if you row reduce it, and it's going to have exactly 1 solution, when you row reduce this matrix, what better you see? You better see 1s down the diagonal, right? Better see the identity matrix when I'm done. Okay? If you know the language, that's called referred to a non-singular or an invertible matrix. Okay? In that case, it means you have a solution. You have exactly 1 solution. Okay? This matrix is always invertible as long as you don't have repeated data points. You're guaranteed that it is invertible. There will always be exactly 1 solution. As long as you don't repeat data points. If you repeat data points, that won't. Okay? All right. However, from a computational standpoint, this matrix is kind of sucky. Okay? Why is it kind of sucky? Well, this requires a little bit more than if you just had just started linear. But if we think about what we're trying to approximate things with, you probably familiar with the term linear combination, right? These polynomials are a linear combination of basis polynomials. I can generate them from 1, x, x squared, x cubed, x to the fourth, and so on. Let's think about the graphs of those particular functions. Well, 1 looks like that. That's super interesting, right? Okay. Y equals x looks like that, right? Y equals x squared looks like that. Y equals x cubed looks like that, right? Y equals x to the fourth, I'm only going to draw the right-hand side, is even flatter and steeper, right? The next one's even flatter and steeper. They're all starting to get smashed together, right? So what happens, pardon me, as you get more and more of these polynomials written in this way, your matrix it's still invertible. It's still non-singular. It still has a unique solution. All of that good stuff, right? The problem is that the matrix gets really, really close to something that is not invertible, because I'm smashing all those things together. If you've heard the terms before, the columns are getting really, really close to being linearly dependent, which is bad for columns. Okay? It makes your matrix not want to be invertible anymore. We refer to this type of a matrix as ill-conditioned. And ill-conditioned matrices are hard to deal with when you want to solve things. Okay? So even though this works, and the examples that we will have, they will be fine, just know that in practice, when you come with large-scale systems, and I'm talking about, people try to solve systems that have millions of variables in them, right? So they have to worry about such things. This is a very, very straightforward way to start. This is not the way people do these things in practice, because they just have bad things happen. Okay. So anyway, how do we solve this? Well, we're not ever going to solve this by hand. Okay. Again, if you've had linear or are taking linear, you're practicing putting these into a matrix equation form, right? So I would have a column of coefficients that I'm trying to solve for. I don't know why I wrote that in red. And then on the right-hand side, you would have your y values, which in this case were 2 and 5.4375, 7.3516, all the way down to 12, right? Okay, so let me show you how you would solve this in Python. I think I'm going to write a smaller matrix. I have to type all this down. You can probably think pretty quickly about how you might write a program to get those entries in your Van de Waals matrix pretty quickly. There's actually a built-in method for doing that in Python as well. But let's do something slightly smaller so that I can show you the Python commands more quickly than typing all these nasty numbers in here, right? So let's say we wanted to do a cubic function. Let's say we use the points. Let's do -1, 2, 3, and 6. And let's say we had the y values of -5, 1, 7, and stop it, 3. I'm just making numbers up. Okay. I'm going to write this on the board also so that I don't have to keep switching back and forth between windows. All right. So the first thing that we need to do is create a couple of matrices. Let's do, I'll just put it in here. Code. There we go. All right. So in NumPy, we can create what are referred to as arrays. Arrays are like lists, except that they're just called arrays, and then NumPy deals with arrays. Okay, so you can create arrays from lists like you would in Python. All right. So in this case, let me call it A for a matrix here. Oops. Remember again that we want across our rows, we're going to have the x value, a 1, the x value squared, the x value cubed, right? We're going to go across. So our first one should be a 1, a comma. Oops, I need to put another set of brackets in here. A 1, and then a -1, a 1, and a -1 for the first row. Because again, your first column is all 1s. The second column is your x value squared, x value cubed, right? So I've got a 1, a -1, a -1 squared, a -1 cubed, right? I've got that, what looks like a list as the first row. Do the same thing for the next one. I would have a 1, a 2, a 4, and an 8. The next one I would have a 1, a 3, a 9, and a 27. Oops. And then finally, the last one would be a 1, a 6, a 36, and a 216. Wait, zoom that cell. Oh, it did. Cool. There you go. Is that a little bit easier to see? Yeah? Okay. I need to do the same thing for the constants that I have. I put this in as a single list here. I had a -5, a 1, a 7, and a 3. Those should enter those in there. If I print, let this go away. If I want this, put it. If I want to see what they are, you can print the matrix here, for example. And you can see it put them in as the rows there. Okay. All right, so I want to solve the system of equations, right? Well, I could have imported the linear algebra solver or the linear algebra commands as a separate, like we did NumPy as NP, but it's the same thing for the linear algebra. I didn't do that, so I need to type it in there. np.linalg will call linear algebra functions, and then solve will solve the system. The syntax is to put the coefficient matrix and then a comma and then your constant matrix. So np.linalg.solve, coefficient matrix, comma, the vector on the right-hand side, and it should, if I've done this right, spit out your answers. Okay. And I know we're out of time, but if this should be your, when we did this should be your constant for your cubic, coefficient on your x for your cubic, x squared, x cubed coefficients. Okay? So you should be able to go plot that and see that that really does pass through those points. Okay? All right. We'll do more of this next time. We'll talk about quicker ways that we can try to get these interpolating polynomials. We'll also do some stuff in Excel as well. Pardon me. So have a good one. Sorry, we're a couple minutes late. I apologize. Don't forget, the second math candidate is here tomorrow at 2 for the research presentation and 3:18 if you're able to go. Otherwise, have a good one. We'll see you on Thursday.